bandwidth. Oh no, actually wrong button, sorry. Yeah, let me know guys if you can see.
Yep, see your screen. Yep.
Right. Yeah, can you see this?
Yes.
Okay.
Yep.
Yeah, so thank you everybody for coming to my presentation. I just want to, I think this is the first time I want to introduce EigenTrust officially to the whole team. And this is going to be very high level, so it's not going to be developer focused. We're not going to focus on any implementation details. It's just high level introduction to EigenTrust and some of the decisions that we made and the problems that we are facing and the future plans for the project. Yes, so first of all, the team. Yeah, so we have two kind of two parts of our teams. So two departments. The Huarang and Armand are working on zero knowledge side, and Alex is working on the client. So client meaning the library that's built on top of zero knowledge circuits, and the CLI, simple CLI that people can use to play around with the algorithm and experiment. And I'm also acting as I'm working on both ZK side and the client side, and I'm also acting as a team lead. So yeah, I was here for one and a half year. Yeah, so the problem that we're trying to solve is that in the traditional platforms, like I don't know, for example, Uber and Lyft and I don't know, Airbnb and similar. So they all have reputation systems built in, but these reputation systems are not transferable to another platform unless they explicitly make that bridge. So usually people have hard time, like people who are a long time on these platforms, they have hard time to switch on other platform if they don't like it. So that's I think the problem that we're trying to tackle. And the way we want to solve it is, in this, in let's call it Web3 industry, we want to build things in layers. We want to build things that are interoperable. So we're trying to do that for reputation. There are a few characteristics. Like first of all, this has to be decentralized and self-policing. So like the protocol has to be neutral and decentralized and permissionless for anyone to join. It should be a reputation layer. So it's actually there's this term reputation bank, which generally means like it's supposed to be cross apps. So multiple apps can build on top of it and use the same reputation in multiple apps, and people can seamlessly switch between them. It's a kind of a central place where your reputation is kept. It's separate from the platform itself. And we're trying to use zero knowledge proofs so we can make compute this algorithm off chain and then use these small proofs on chain for some useful things, which I'm going to explain later. Privacy. So also it has to be private. There are three problems of privacy. privacy of identity or anonymity, which we are just a second, which we're trying to solve. The privacy of the scores, and which is the privacy of the reputation scores of each participant in the network, and privacy of the graph, which means that privacy of the connection. So, like for example, on I don't know, let's say some social apps, some people have a lot of followers and a lot of interactions, and even though their anonymity, their identity is private and their scores are private, it still make them a target, for people say, hey, this must be some interesting person. Let's track them and see if we can figure out who they are. Yeah, the stars means that it's work in progress. So yeah, we have ZKP is almost ready, and like it's interoperable by design. So yeah. So the concept of attestations. So this is all coming from like the beginning. In the beginning, we have the concept of attestations, on top of which we are building our protocol. So attestation is attestation system is kind of a data layer that for us, so some kind of place where we keep all the data on top of which we calculate reputation. So some of the properties that it should be peer-to-peer, so it should be one peer should give attestation to another peer directly. So yeah, also I want to mention that the concept of attestation. Attestation is some kind of statement that one peer can say about another peer, and also sign it with their private key. So it could be anything in the social network terms. It could be even reactions to some post, or it could be it could be comment in some, I don't know, let's say ride sharing apps. It could be a rating, so rating like about the ride and stuff like that. Like currently we have one rating per domain. I didn't explain the concept of domains. So domains is like it's kind of like separate graph. So for example, there's each domain for every for example, let's say ride sharing domain. So like it should be shared between all the ride sharing apps. So yeah, it depends on the context. So domains are built on top of context. So like it could be context of social media, so you could build a domain on top of social media. It could be reused on top of reused in multiple apps. For now we are storing this attestation on attestation station, and it should be, I think it's already deprecated. Like things are moving fast in this field, so people move to Ethereum attestation service, and we are trying to soon. And also like I mentioned, like there's everything can be attestations, like comment, like rating. So, and all of these need a separate schema to describe themselves accurately. And what we did, we created some initial schema for giving rating to some user. This is just the initial schema that we use for making experiments, but in the future we should support many schemas. For now, schema is a mapping. So like first there is a tester, the peer that's attesting, and so it could be peer 1 here, and attested is a peer 2. The key is some identifier for this rating, and the rest are the content of the payload of the attestation. So the payload consists of the ECDCA signature, which is actually here you can see how they're made of. So like, first of all, key, it contains of some kind of prefix and the domain I mentioned before. So the context in which you're giving attestation. So signature S and signature R and recovery ID is just ECDCA signature of the Poseidon hash. And for Poseidon hash is the pre-image of this hash are these four values. And the message is some kind of actually, first of all, the value is the rating itself, and the message is just some kind of metadata that peers can use to give more context to this rating. You know, why if they give low rating, they can explain why, or if they give high, they can also explain why. And this is some kind of, this is how the correlation between this data and the pre-image that we calculate this hash off chain and sign it off chain and put the this top layer on inside the smart contract. Then what we do is we have these attestations inside the smart contract, and what we do is we download all of them and create a set. So the set consists of every peer that's participating in this domain. So every peer that's either a tester or the attested. So we kind of query the blockchain and create this set, and we fill the null for the places where we don't have any peers, or because we have to have a fixed amount of sets we defined beforehand. And if we can't fill the set, we just fill with null for the rest of the peer. So then we take the values. So like these values here, we take them and we create a matrix from them. So these are the ratings from peer, for example, from peer 1 to the rest of the set. So they give rating 32 to the peer 2 and rating 68 to peer 3. And they cannot give any rating to themselves, which is why this is 0, and they cannot give rating to obviously 0 peers. So we do some kind of filtering to check that inside the circuit. And the last step is normalizing. So you normalize each row. So like you take the sum. Sorry. Is anybody asking questions? No? All right. We normalize the score. So we take the sum of on each row, and we divide the score by the sum, and we get normalized scores. And these scores are actually the inputs to the Eigen Trust algorithm, which is I'm gonna explain now. I try to visually explain how Eigen Trust works. So like, first of all, you can see these 3 peers that were in the previous slide. And you can see, first of all, this is their initial score. So like they have there is a concept of initial score, which is 1000 for every peer. And this here is their attestations. So like how they divide, this can also be seen as a percentage. So how do they divide their initial score? So you can say 32% from peer 1 goes to peer 2, which is, this is peer 2, and 68% goes to peer 3. And you do that for every peer, for several iterations. So let's focus on just one peer. Let's say peer 3, which is highlighted in green. So you can see that peer 3 receives 68% from peer 2 and 68% from peer 1 in iteration 0, and you take the sum, and this is their score in the second iteration. So yeah, we do that again. So obviously everyone has different score in the second iteration, but we do that again, like we divide by the same ratio, same percentages. Yeah, and you can see in the second iteration it has a different score. And if you do this for several iterations, the scores start to converge, and they don't change after that a lot. So this is how it looks like. This is this array here is a initial score, but you can see that it doesn't need to be the same for everyone. So here I used different for everyone, like here 1000 and here 200. But yeah, the idea is the same. So when you apply the opinion matrix, after several iterations, the scores start to converge, and after you can see iteration 7, it doesn't really change from iteration to iteration. And yeah, and depending on how much precision you need, you run more or less iterations. Yeah, so it leads us to some problems. So like if we imagine like we have a network where everyone has initial score, everyone is like who is participating has immediately from the start some kind of initial score. What they can spin up a lot of bots and give attestations to themselves, and that way collect a lot of reputation scores. So there are two solutions that we're exploring, like Sybil rank, which is this is very in early stages. We're supposed to solve it by analyzing the graph and seeing who is actually doing that, who is actually just having one neighbor that's themselves and collecting scores from those low quality neighbors. And the second solution that we also explored is bootstrap peers. So bootstrap peers, it means that instead of just giving everyone the initial score, you choose for every domain, you choose one person to have initial score, and here we just chose peer 1. But the problem here is that everyone has to be connected to this peer 1 in order to receive reputation score. So they either have to be directly connected or indirectly. So you can see, for example, this peer is indirectly connected to peer 1. So that's why they have 3 degrees of separation between peer 5 and peer 1. So yeah, that's why for the first 3 iteration they have 0 score, and then they jumps to 63, and then again, and you can see that the last 3 it doesn't really converge, but it would converge if we run it more iterations. But that means that we have to build bigger circuits if we have more iterations. So we are trying to see more, look for more optimized solutions. So I want to talk about applications of this algorithm. So we can use this for I see 3 main applications, like for governance in communities, for community gatekeeping, and for marketplaces. So for governments, meaning doing reputation weighted voting. So each participant should give their vote, so their vote should be weighted by the actual amount of reputation they have in some DAO. Or it could be threshold voting, so only the peers who have score above some threshold, they are eligible for voting in some decision making. And also, this threshold checks can be used for community gatekeeping, so you can only join some community if your reputation is above some kind of threshold in a certain domain. And yeah, marketplaces where people interact, peer to peer. So like they exchange goods and services, and they rate each other, based on how good the service is. Yeah, that would be, very similar to, how it's used in traditional platforms. Yeah, so I'm gonna try to show you a small demo. So I have, I'm gonna hope you can see this. I'm having Unreal run here, and I'm gonna try to first deploy the attestation station contract. Yeah, so it's successfully deployed, and I'm gonna try to give attestation to 2 addresses. So let's say first one, if you look at here, so we are attesting to this address, and we are just rating them, giving it a rating of 20, and we are not, including any message, so it's kind of excluded. Yeah. So the transaction is successful, and I'm going to try also to give to another address another different rating. Yeah, and now I'm going to calculate the scores. And yeah, we have a file that we save, which is this file. Yeah, so you can see like this is the address that I used, and these are the 2 peers that I attested. So I have my reputation hasn't changed from the initial one, but the other ones did. So like we have the peer who we attested with higher score has bigger score at the end. This is I don't know if you can see. This is actually the scores. Yeah. So if you wanna play with this CLI tool, like it's very much work in progress, so you should contact me or Alex to help you with this. But yeah, I want to talk about the future. The last slide, which is we have three directions we want to focus on. So like first of all, like making a decentralized. So right now this is not decentralized, so this is like a just zero knowledge proofs and this CLI tool that people can use. Also library that developers can use to build something on top of. But if you wanted to make some kind of service that people can just plug into and through the API, it should be some kind of decentralized network, which also solve the censorship resistance. So like if it's decentralized, and also solves the horizontal scalability. So like we can parallelize the proof computation between the nodes of the network. Second problem is like privacy of identity, privacy of the scores, and privacy of the graph. So yeah, we're very early stages here, but yeah, we want to solve privacy in all these fronts. For identity, maybe we could use semaphore to use identity commitments instead of addresses, and yeah, stuff like that. For the scores, we have to use some kind of encryption. We're not sure how to achieve that. And for the graph, we're not sure. But for scalability, for vertical scalability, like for like in an example I showed, like they have just 4 or 5 participants, but we want thousands or hundreds of thousands of participants. So you have to make more efficient zero knowledge circuits, and we can do that by utilizing aggregators. So splitting the circuit into several parts and kind of try to parallelize the computation. If anyone has any questions, here you can join our Discord server that we have just for the Eigen Trust. And I want to thank the Ethereum Foundation and the PSE team for making the conditions for this project to start and giving us the freedom to work on it in a way we want and like in a pace that we like. Thank you so much.
Very cool presentation. Thank you, Filip. Now we can take question. Anyone feel free to unmute yourself and ask question, or if you want to type it out, you can use the chat as well. So I do have a couple questions, but I'll let other people ask. Okay, everyone being quiet. So my first question is the attestation. So it's upon the application to define when will it be a test, right?
So different applications will have different schemas. So like if you want to build social network, you will have a different schema for interactions, like either it's some kind of comments or reactions of follows or any kind of interaction. So first of all that, but also application has to define who do you want to attest to.
Okay.
And scores, and also whether it's like it could be scores can be also binary, so it could be binary and also could be so some range like we used in our schema, like from 0 to 255. But it could be 0 to 5, or it could be just 0 and 1. It could be just positive and negative.
Okay. And the in one of your slide, you have this field of a set. So set is like 3 peer and plus 2 node there. This is also upon the application to decide how many they want to include that set, or?
It could be. I think we're gonna have to do that, but like ultimately we want to like support like very big sets where like we want to include every participant, but in kind of a short term, I think we want to build some kind of way so that like communities can kind of limit who can join this domain. So like, I don't know, for example, create a Merkle tree where people can join this Merkle tree, and only like until only the leaves of the tree are kind of can be the participants. If the tree is full, then no one else can join, and so we kind of have to create some group functionalities that people can join and leave the groups, and these groups has to be limited by certain amount of participants, which all depends on how much we can put in the circuit, how much we can scale.
Okay. And the attestation, so your team are thinking to use the Ethereum attestation station for the attest, or you guys already build a algorithm for it?
So we wanna use so we're gonna switch to Ethereum attestation service. I think I'm gonna show you.
I'm asking this because in Unirad we are looking for a way to simplify our attestation. So I would like to hear you guys' idea too.
Yeah, so we wanna use Ethereum attestation service, and we want to figure out a way to support as many schemas as possible. So yeah, and on EIS, like people can build their own schemas, and they are very different. So like we have to think about how do we create a way to process these schemas, like how because they are going to be all different, and they would need, each of them would need different kind of validation.
Okay. Yeah, very cool. How about other has any question? I guess you guys not like me. I'm
Right. Yeah, thank you guys for listening. You can reach out, you can join the server and ask any question if you want. Yeah.
Yeah, it was great presentation. Thank you very much, and thank you everyone to join. See you next time.
Yeah, thank you.
Thank you.
Thank you.
Bye.
Bye bye.